right as the music ends. Let's see, how am I sounding? How am I horribly delayed? You way behind?
You sound good.
All right. Well, as long as the sound is good. Delays are delays. So let's see. Is that the page I wanted to start with? Probably not. Let's see. Is it? Well, we can. That'll fix that. Can't. Ugh. I felt like I'm so in a hole when I put both of them on.
But you sound good.
All righty.
The grain is behind you, but
A little bit. That apparently is acceptable by today's video standards. There we go. Hey-o, and welcome back. Today we're going to be talking about passing parameters in assembly using our Yup 5108 virtual microcontroller. That sounded like a decent intro. All right, we'll go with that. So, all right. So in case you're new here, the Yup 5108 is a virtual microcontroller that I designed from the ground up using an 8-bit system meant to look very much like the 50... Dang it. Drawing a blank. That's right. Okay. Dyslexing my own numbers. All right. So it was the Yup 5108, and it was designed after the 8051 microcontroller, an 8-bit microcontroller from the late 70s, early 80s that I first started learning assembly on back in the day. So as a quick review, the microcontroller has 3 8-bit registers labeled A, B, and T. Sorry. A 16-bit register, which is a data pointer to either RAM or ROM, a stack pointer, which we'll get into later on in this video, an instruction pointer, which is essentially what location is the next instruction to execute, and then down here we get into the sequencing of the internals of the processor. We won't deal with that detail today. Just suffice it to say that each of these locations are what is referred to as registers in the processor. And by and large, most parameter passing from one part of a program to another is going to be by passing values through these registers. So if you want to get into see some more details of all of that, we have a whole series of videos on the Yup 5108, all the way from writing hello world directly in machine language, what a pain, to actually creating a print function. And that's kind of what we're talking about today, because in this video a year ago, I failed to point out how we got the information to the function to print, and pretty much just glossed over the idea of the parameter passing. So that's all up on the YouTube channel under our 5108 playlist, and be sure to like and subscribe and all like that. We won't get into that too many times, dude. That's just annoying when people get too obsessed about that. But anyway, alrighty. So all right. So back on the processor diagram here of all the registers. So, oh, loud noises. That's okay. All right. So back on the processor diagram, each of these register locations are used for a number of different functions within the processor. And a processor does really 2 main things. It moves data around in memory, makes copies of it and moves it around, and then also does some calculation like adding 2 values together, multiplying 2 values, that kind of thing. And in our case, our processor can only add and subtract. So for multiplication, we're going to repetitively add, and for division, we're going to repetitively subtract. And to do that, we want to pass in a couple of numbers and say compile them. So Rather than doing this all in machine language, we now have a assembler, and that allows us to write in an assembly language, also of my design, but not surprisingly very similar to most of the other assembly languages out there. Yeah, let's see, where's that? Never mind me while I'm staring, looking for my sources. All right. So this assembly language consists of a very simple set of commands, a comment character, and include other, a source file, setting the location of the objects, or setting the location of the assemblers, um, blah, 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 setting the value of internal assembly, blah, setting values of the internal assembler addresses, and constant strings and the like. We won't get too far into it. It's more readily understood by demonstration than explanation. So let's jump back over here. We have our program written in our assembly, and this is the grid of documentation of all of the assembly instructions. So these are the actual instructions that the processor operates on. By and large, all of this light blue area are move instructions, copying from one location to another. Down the diagonal are all the system instructions, like incrementing the stack pointer, decrementing the stack pointer, and function calls, and more importantly, conditional function jumps. Blah, 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 blah. Conditional function calls and conditional jumps. Actually, I guess it's all just conditional jumps. Yes, all conditional jumps. Uh, see what you get when you don't write a script. So, all right. So for the very first portion of parameter passing, we're going to use the registers. And for that, we've written our simple program. Doesn't do much. It's going to start here. Wait, how do I explain this? So our first program is parameter passing via registers. And when writing, yes, the first line of every one of the assembler programs is a write of the function that we're going to start at. Generally, it's called main. So basically, I'm saying here, put the address of main in the first 2 bytes of ROM, and that's how our processor operates to find where it's going to start when it boots up. So we write that address. This is where we define that address. It's the main program entry point. And then we start executing individual assembly instructions, some with parameters, some with not, some without. And that is pretty much the extent of assembly programming. Well, there's a couple extra details. A couple extra details involved things like creating a variable where you want to store some information. So in this case, we're going to take 2 values, AB and 3. We're going to load them into the system, call a multiply function. When that multiply function returns, we're then going to create a variable, although it is already created at boot up. We're going to say that variable contains 2 bytes, and then we're going to proceed to copy the returned value into that variable. So let's take a quick look at that and how, let's go ahead and take a look at how that works. So first we're going to quickly compile, or rather assemble, our program. Then we're going to start our emulator. So this is kind of designed off of an old 90s system emulator. where again we have our A, B, and T registers, our data register, stack pointer, instruction pointer, our instruction register, and all our I/O ports. Again, all of this over here has to do with the sequencing of the processor for individual instructions, and we won't get into that today. So we're here at the start of main. If we single step, we'll get to where their first assembly instruction, which is load into A from EEPROM, the value AB. So here we are in ROM, based off of our instruction pointer. We're at this instruction, it is load into A from E, and there's the value, the next byte in E or EEPROM or ROM is AB. So we're going to go ahead and load AB into A positively instantly. Then we're going to load into B from EEPROM again, the value 3. And sure enough, there's a 3 in our EEPROM. Seeing a flash happen on this other screen. Anyway, now that we have a value into A and B, we're going to call a function called multiply B and A. And it's called that because the result is going to be in B. Now we're going to call our multiply function, which is mul_BA, which will multiply AB times 3 and put the result into the DR register. So let's go ahead and step into that function. Here's the definition of mul_BA. First thing it's going to do is load into T the value of B. So we put our two parameters in the A and B register. Now we're going to copy it out temporarily. And the reason we're doing that is because when we load anything into the B register, it resets the register non-zero flag. And we'll see why that's important in a minute. So first we temporarily store off B into the T temporary register. Then we're going to zero out the DR register, since that's essentially initializing our return variable. Then we're going to load into B from T, and that resets our non-zero flag for us. So now our next instruction is we're going to jump a long distance versus a short distance if the non-zero flag is set. And this is essentially how almost all operations, conditional operations, happen within computers of this architecture. Essentially, you do a calculation or it'll either be a register load, such as this, where anything loaded into B is checked for non-zero and resets that flag, or it will be set based off of the calculation in the ALU. For example, if you subtract two numbers that are the same thing, you end up with a 0. And if those two numbers are not, or anything other than equal to each other, you'll end up with something other than 0. And because of that, you can very quickly decide whether what the person typed in was a particular character or what have you. So long story short, we're going to jump along if there is non-zero from this location to this location. Really, it's just jumping over this next instruction of return. The reason we're doing that is because obviously if B happened to be 0 and we multiplied something by 0, we already have 0 in our return register, so we can just simply return because the result would be 0. That's not the case now. Whoops. That's not the case now, so let's just jump over that. Now we're going to sum the contents of the register D and the register A. So we're going to add A to D, D being the destination. So now we've got AD, we decrement B to count down the number of times we're going to add AB to DR. So we're still non-zero. So let's jump back up to the top. Add the value of A back to D again, or DR again. Decrement B. Jump back up. Add the value. Decrement B, except now B is 0. So the flag is not set. This conditional jump fails, and we go to the next instruction, which returns back to our main calling function. And now we put in B and A as AB and 3, called multiply BA, and our result is in the DR register. It's done this way because we're multiplying two 8-bit numbers, and so it helps to have a 16-bit number as a destination. But now it's in this location, and we're going to use this location for other functionality. So we have to save it off from the registers into someplace in memory. In this case, we created a variable here called product, gave it 2 bytes of space. So now we're going to temporarily store off these two values into A and B. So we're going to load into B the value from R. So this 1 got copied over to there. Now we're going to load into A the value from D. There's our 2. And now we can load up the location of our so now we can load up the address of our variable into the DR register. It's 0006. And we can store the B value, the lower byte of the DR register, at location 6 in RAM. We're going to increment the DR register. So now we're pointing at the next byte in memory. And we're going to store indirectly the value of A. So A is a 2. We're going to look at location 7 in memory, and we're going to copy it from here to there. So now that's essentially saying variable product equals the DR register. But we have to make some couple of little moves in between in order to make that happen. And now we're going to go ahead and print the result out. So we're going to load the product variable back into DR. We're going to increment that because we want to look at the big endian when we print it. So we're going to look at location 7. It's a 2. We're going to load that LBM, loaded that 2 into the B register, and then we have this function called print B in hexadecimal. And I don't want to get into the details of that function, just suffice it to say that it turns the hexadecimal value in the B register into 2 printed characters in the terminal. So that gives us the O2. Now we're going to load the address of product again, load the first byte instead of incrementing, and again call the print. So 0201 is the result of multiplying those two values, which I forgot already, is a result of multiplying A, B, and 3. Well, let's go ahead and confirm that just to make sure our calculator or computer is operational. So let's go ahead and confirm it. AB times 3 equals 201. What do you know? 0201. Same thing. All righty. So I think you get the idea. These very few handful of register locations make a convenient way of passing data back and forth from one location in code to another. However, they're limited. There's only 2 that I can use because the T register is actually used as part of the transfer, as part of this call to another function. The T register gets overwritten. And these are the kinds of trade-offs that are made when designing a processor, and you'll see them if you look at a number of different 8-bit processors. There's a number of trade-offs that have been made. One of which, in this case, is the T register doesn't survive function calls. The T register is also used for the increment commands. So if you increment A or B, T gets set to 1. So number of trade-offs. All of those trade-offs, luckily, are documented here in the 5108 User's Guide, which includes a description of the general operation of the processor itself, as well as design considerations, the layout of all of the sequencing logic in the processor. And this goes along with the sorry, I didn't have this up. This goes along with the Do 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 do. Come on, 100. And we zoom in, and here it is. So all of this goes along with the electronic diagram for the processor, which was built in Logisim Evolution. This is the logical model of it, not the electronic model of it. But this is where I started and sort of zoomed out from here. From that to a computer view where this is the processor and there's your screen and such, to a full desktop view as if it were an old monitor or a dumb terminal type system. But to get anything useful on a system like that, you need to be able to write in assembly, at least, if not in C. And actually, there's a small C program out there called Sector C, and it's supposed to put an entire C compiler in like 512 bytes. So I think I'm going to port that at some point, and it'd be really cool to be able to write my own C programs for my own processor. In any case, back to parameter passing. All right. Let's see. This we want to close. And let's get to parameter passing 2. All right. Let's see. All right, we're back. So next we're going to get into parameter passing using what in effect is global variables, which are by and large verboten these days. But in a small program, when you have a small amount of RAM and it's very dedicated, and like most embedded systems are, globals have their place. So here's our next program. We're going to start off just simply writing our starting point like we do all the time. We're going to include our utility functions, our string functions, just things that are already around. So utility functions print things out for us. The string functions manipulate strings of characters for us, things like that. So now we're going to define our main entry point, and we're going to define a couple of variables, the X variable and the Y variable. I know everybody hates me, but it's location 1 and location 2, however you want to call it. And each one of those locations is going to be a single byte in size. Now, again, as I said before, many of the times these things are much better demonstrated than explained. So now that we have our program, let's go ahead and quickly assemble the program and bring up our emulation. So again, our emulation shows all of our registers in our processor, as well as a line of memory and a line of ROM, well, ROM and RAM. And those are the lines of ROM and RAM that are around the addresses that are currently set up in the stack pointer, data register, and instruction pointer. So if we start our program, we're starting on line 20, and it says we're going to initialize the processor, and it's going to read this location and then jump to that location. So big surprise, it jumped. Oops. Eh. Don't you hate when that happens? You hit the one wrong button. You're hitting my buttons, Roger. All right, let's start that again. Let's compile. So we bring this up in the emulation, and we have our program first starts off with saying where we want to go, or rather, the processor starts up and everything's at 0. So the first thing it looks at is the location in ROM at 0 and says, what do I do with this? So as a convention of the processor, which different processors do this in different ways, these first 2 bytes in ROM are where our program is supposed to start in ROM. In this case, it's just a few lines later. So we're going to hit the wrong button again and start this over. All right. That button. Then this button. That is not the right button.
12 seconds off.
12 seconds. Oh my god. Hmm. All right. Don't you hate when it does exactly what you tell it to do? All right. I'll explain in a second, but we'll probably chop all this out later. So it did exactly what I told it to do. Here's main, the location main. I say start there. Well, here's where main's defined. And the next 3 lines are already, I don't know, it didn't do what I thought it was going to do. Don't you hate when you think you did what you thought you did and it didn't do what you did? But you did do what you did do? I don't know. All right. Let's try this one more time. All right. Do a quick assemble. We then bring it up in the emulation. And then we are saying we want to start at main. Here is main. And the first instruction after the symbol is this. We're doing it right this time. So this instruction is load into the A register from EEPROM the next value in the EEPROM, or ROM, depending on how you want to look at it. So you can actually see the instruction here in the ROM, and the next value is AB. And since we're going to load into A, the next value, we're going to take this AB and make a copy of it over here in A. And boom, there it is. Pretty straightforward, right? Next instruction, load into B, again, the value from EEPROM, which in this case is a 3. So now we have A, B, and 3 all loaded up in A and B. Now we're going to jump in to the function called multiply B and A. And since we don't have a multiply function, again, we're going to add it repetitively. And I just realized that I started the wrong one. All that getting the wrong buttons, I tell you. Go away. Parameter passing. We already did this one. That's what I'm supposed to be on. Yay. Yay for the wrong one. All right. Fix it in post. All right. It's fun because it's just you and I watching.
Yeah.
So it doesn't really matter.
But other people are going to watch it.
We'll figure it out in post. All right, so now we're on to parameter passing number 2, and number 2 describes passing variables in, or passing parameters rather, in variables. And because we're in a fairly simple environment here, pretty much any variable defined is a global variable and can be reached from anywhere in the program. And there's some good reasons for that. It's primarily because you don't have a lot of memory to work with, and so a lot of times you'll reuse the same memory um, as a quote unquote global variable. But there's ways around that and ways to improve on that, and one of those is the stack, and that will be coming up right after this. So now let's talk about those global variables. Again, we will compile, and we're going to bring this up in the emulator, and we're going to say go to the main assembly program, which is right down here. And right after main comes two declarations in the assembler. One is to create a variable named x, make it a whole 1 byte in size. Then create a variable named y and make it 1 byte in size. Now, obviously, in modern computers, your variables names can be very long, so you could make it all sorts of meaningful variable names. But for convenience, we're just going to use x and y. So now that we have those in place, we're going to do the first instruction, which is load the address of x. So the address of x was located at 6 in memory. So we're looking at 6 in memory here. And we're going to load the value of, or actually, so first thing we did was load this with the address 6, which is the address of x. Now we're going to load into A the value AB. So now we have AB and A. We have the address of X in DR, and now we're going to copy from AB or A into DR and copy that into memory. So all of that is the equivalent of this in the C language, where you say X equals this value. That's essentially what we did here. We loaded up the location of where X is in memory, and we loaded up this constant value, and then we pasted that constant value out to memory. We'll do the same thing with y, load the address, load a constant, load that constant into that address. And so now x and y are these two locations in memory, and they have the value we're interested in. But since we used a and b to get those values there, we now need to set them back up the way they need to be for when we call multiply. So now we're going to load the address of x into the DR register, copy what is in memory into the A register, load the address of Y into the DR register, load the byte that's pointed to by the DR register into B, and now we're going to call the multiply BA function again. We did this before, basically runs through a loop, so we're just going to jump over that function now, and you'll see we've created another variable called product. And this is the result of multiplying two numbers is referred to as the product, and it could be 2 bytes in size. So our next instruction, we're going to take the result of our multiply is here in the DR register, because that's how it passed that value back to us. And we want to use that DR register to move these bytes and put them somewhere so we can look at them later. So the first instruction we're going to do, or the next instruction we're going to do, is called LBR. That is load into the B register the value that's in the R register. And if you hadn't guessed by now, the DR register, these two bytes, or this byte is the D and this byte is the R. So LBR will take this 4 and stick it into B. Then LAD will load into A the value from D. So now we've copied this value from DR into A and B, and we can now use DR to load up the address of memory where we want to store that value. So the address of product in memory is 8. And now we're going to take these 2 bytes and store them out. First, we store the B value, which is the lower byte, because we're little Indian, the appropriate correct Indianness. Big Indian is wrong. But we read it in Big Indian, so we do some manipulations to correct all that, or straighten all that up. So now that we're done that, we're going to store A. And if you see, we've got those two values, that 08 and 04, are now in memory at this location, stored little endian, the littler byte first. And now we're going to go ahead and print the entire function. So to print the whole function, we're going to load the location X into DR, load into B from memory, which is to say load into the B register from RAM wherever this is pointing at. So we're going to load that AB into B. And now we're going to call the print B function, which just takes this B value and puts it out on the terminal here. Then we're going to write to port 1 from EEPROM, which in this case is the lowercase x character. And if I hadn't explained really, but of these ports, you may have seen these port numbers change over time, or you're about to see one change anyway. Because as we write the lowercase x, it happens to be a value 78, and we're sending it out port 1, which is essentially the monitor port. So port 0, we read characters. Port 1, we write characters to this serial area. So now we're going to load the address of Y, which is B6. Oh, no. I'm sorry. I skipped over the print B function. So basically we loaded Y and printed it all in one big step there. Now we're going to print the little equal sign, and we're going to load the address of product, which is 8. But because we're little endian in memory, but we print everything in big endian, we're going to increment the address from 8 to 9 and print the big endian value first. So we're going to load that value into B. Then we're going to call print B. Now we're going to load the address of product back into the DR register. We're going to then load that value into B from RAM and then call print B again. And so we get the formula AB times 0C equals 0804, all in hexadecimal. I know it's like milk, isn't it? Like clear as milk. Well, if you read and write hexadecimal, it's second nature after a while. So the next instruction is actually to print out a carriage return. So we print the carriage return and then we halt. So those are the two well, let's see how to say this. I think by now you're getting the point that passing by register is useful only for really small functions that do very limited things. And then once you start wanting to do more and more functions or pass more and more data, you're going to have to use either global variables or the next thing, the next great invention in computing, the stack. And the stack is a block of memory where you can use 2 or 3 bytes or some number of bytes of that stack memory and then give it back when you're done using it so that other people can use it. And therefore, you don't need to constantly create more and more global variables for every function that you create. And it's also the primary methodology of being able to pass values down to a function, that function manipulate those values, and then pass those values back up to you, all of which is done in a way as to not constantly draw more and more total memory. That's more or less what I wanted to say about that. That's about all I got to say about that. So, in any case, all right, let's clear that up. And parameter passing number 3. So parameter passing number 3. We have much of the same program already done that we've done before. So we're going to actually only initially single step just to go from main. And again, we're doing the usual loading the address of a variable, putting a value in that variable, storing that value into RAM, load the address of another variable, load a constant, store that constant in that variable, load the address of the variable, get it into the A register, load the address of the next variable, put that into the B register. And then again, we're going to call multiply B and A, but this is much bigger than just 3. It's C, and C is bigger than 3 by a lot. Well, by 9. Yes, by 9. I still had to do the math. All these years, I still can't count in hex quickly. So we're going to call the mul BA function, and because it is a C number of loops, we're just going to step over it real quick. And trust me, AB times C is 0804. If you don't trust me, we'll get out the calculator. There we go. And the calculation is AB times C, which equals 0804. What do you know? My computer can calculate as well as a calculator. You would want it to do that, right? All right, so we did the calculation. Now we have the product. We're going to get the product out of the DR register back into the variable like we did before. Print that out. We're going to load up Y. Oh, I stepped into the print function. Well, see now why. Because each level of function uses just those same registers over and over again, it really isn't practical to constantly pass values by register. Obviously, more modern architectures with bigger amounts of memory and bigger baseline size, like 32-bit machines, they have different architectures with much more register space to share. But in our case, we have a very limited amount. We have to do a lot of byte juggling. So let's just go ahead and jump right out of this. Go back to printing our equal sign. Load up the address of product, increment to the next byte, load that byte into B, print that byte from B, load up the address of product, load up the byte that it's pointing to into B, and then print that value out of B. There we go again. So pretty much the same. We're going to go skip all that and get down into here. And this is where it starts getting a little more interesting towards what we're moving forwards. This is where it starts bringing into the concept of the stack. And is it though? No. So this is a more complex version of passing values by globals into functions. So in this case, we're going to print a particular location of RAM and print out a sequence of those bytes. And what we need to do is we will need to, in this case, we're creating a constant, which just basically says, oh, dang it. Reset back to 1. Parameter passing 3. I'll better explain this. All right. I got us all reset. All right. And again, I hit the wrong button. Pushing my buttons, Roger. Oh, I see what it's doing. All right. All right. Launcher again. There. All right. So we get to that point where we've already printed it out. And so for a more complex version, not complex, for a more realistic version of using global parameters for parameter passing, global variables for parameter passing, what we're going to do is call a function that prints out one of the last lines of ROM, or RAM rather, much like this does. But to do that, we need to pass it a location in RAM that we want to start at, and a number that we want to print out, and a number of lines that we want to print out, etc. So we have to send more parameters than we have registers for. And because this is a function that's probably only going to be called one at a time, in other words, there's not going to be two people trying to call this function at the same time, having global parameters for this function is a reasonable trade-off. So what we did at this point is a couple of things. We created this constant, which is the last RAM line, is the address to start at. We then load that into DR with the LDR command. And then we're going to load into A the value D. Oh yeah, that's what I need to say. Okay. So it's actually one of the newer features of the assembler that we have the concept of constants. And those constants create symbols, much like a variable or what have you, but they don't take up any space. They're only used inside the assembler. So in this case, we created the constant last RAM line and gave it the address of FFF0. And that's because we're going to print the last 16 bytes of RAM. And so we load that value into the DR register. We then copy the value from the DR register by copying it into A and B. So now we've got DR into A and B. And that's so that we can load the address of the dump start global variable, which is 3. And then we're going to store that FFF0 in that location. Then we're going to load up the location called dump lines. And we're going to load a constant of 1 into the T register. It's one of the features of the processor that we can load the value 1, 0, or FF into any register without having to load it separately or dedicate RAM, or rather dedicate ROM to loading those constant values. So we load a 1 into T, and then we're going to sit on it. No, I'm just kidding. So what that's going to do is that's going to store indirectly the value T. So we're going to take the value T and we're going to store it in RAM wherever DR is pointing. In this case, that's where DR is pointing. So we copy that 1 into there, and then we're going to call the function DRAM dump. So let's step into that function. You'll see that the first thing it's going to do is load those locations that we actually, the first thing it does is load this little string so that it can print out this nice little header information, which is all of the locations in memory and so forth. Then we're going to call this function that prints out a nice line for us. Another carriage return. Now we're going to read the dump start and dump line variables that we had set up before we called the function. So we just this function knows that these are the two locations that it always goes to for its information. So we're going to load dump start into DR. Then we're going to call LAM, which is load into A whatever's pointed to by this DR value. So that gets our F0 into A. Then we increment DR to get to the next byte. Load FF into D. We're actually using DR to load up DR. Then we move A back over to R, and that's sort of a little 3-step or byte swapping 2-step to get to a value that is pointed to by the DR register into the DR register. Kind of a long way of referring to dereferencing, but So now that was our start location, right? So now that we have our start location, we're going to go ahead and call print B. So we have FF was our in B. So we go ahead and print that value out. Then we're going to load the dump start address again. And right. The reason we have to load the dump start address and then call print for one value, then we have to load the address again. This is all because in order to print the value using the print B function, we override the DR register. So that's why we have to reset it each time. And I hit the wrong button yet again, but it worked. All it did to do in between is it loaded the value and printed that the F0. So now we have FFF0. We can write a colon out to the screen. Again, load the address of dump start. Now we're going to load into A the value 10 or 10 in hexadecimal, which is 16. So A is now 10. And now we're going to call the function dump RAM. So we're actually one function calling another function. And what dump RAM does is, well, I'll show you. It is going to take the values that were passed to it in the DR register and put them in its own global variable, which is where it normally starts. So we store that off. Then we're going to store off a value that was A. We remember we put 16 into A just before we called this. So now we're going to store that value into a global variable used by this function called dump RAM count. Obviously, this is not the most ideal way of doing things, but it gets the point across. Well, hopefully it gets across. Now we're going to load into B the value of A. Basically just copy that over. But that set our non-zero flag, so we know that B had something other than 0 in it. So because it had something other than 0, we're going to jump down to this next symbol and start executing there. We'll load up our start address. Then we're going to load 1 byte from that start address into B, which is 0, of course, right? Because we're looking at the last page of RAM. So there's not much to see there. Nothing to see here. These are not the bytes you're looking for. So go ahead and call print B. And then we're going to print basically a space. Well, exactly a space. And then we're going to do it again, but this time we're going to load the dump start address so that we can add 1 to it and start looking at the next address. So we load that, then we increment DR. So now we're looking at FF1. But because we're going to use this, we need to store that value off. So we copy its from value over into AB, load up our starting address, and then store those 2 bytes off. And then we can load our dump RAM count. Put that into B. Now we have 16. We can decrement B and then store that back off so that we can know how many bytes we've written. And because B was stored, the last thing we did was load into B and store it off. We still have this non-zero flag set, so there's more to do. Load the starting address, which is now the next one, which again is, oh, jump out of that, which again is a 0. So one way we can sort of speed this up is just every time we return from a function, you basically get another character of RAM printed as we increment through all of the bytes now. Let's just jump through all of those. Oh, we start getting something interesting. So we actually get some bytes here with something in them other than 0. And what this area is referred to is the stack. And it's referred to that because the last thing put on it is the first thing that comes off it, just like a stack of paper. And that area is used as temporary storage for information like where to go next or where are you at now. So in this case, our stack pointer is at FFFB, and that is the last location that we left from, which is to say, every time we jump one function lower, we have to store where we were last in order to come back to that spot when we're done with that lower function. And those locations are stored here on the stack. I think that's what I wanted to say. Oh, these segues are the hard part. Actually, there's a little bit more to this, and that is to print these characters out as if they were text-based. So let's just go ahead and let her rip until she's done here. All the way to the halt. None of them were printable, not surprisingly. And now you'll notice that we've come back all the way up out of the program, and our stack pointer is now at FF. I guess I haven't really gotten into that too far into when we call a function. Yeah, what's the process of the function call itself? All right. Let's see what else we want to do. All right. Mm-hmm. All right. I forget that it was in the same program. This is a bit of a jump. All right. Guess this was a bit of a script that I wrote at some point. God forbid we have a script, huh? All right. So now that we've passed everything with the registers themselves for simple functions or globals, which give you a lot more that you can pass back and forth, but really doesn't scale. The next or the final method of passing parameters is referred to as the stack. And like I said before, the stack is a block of memory that you get to reuse for different functions and therefore not use up all your primary memory. And part of the reason it's there is because we only have one 16-bit data pointer register and two 8-bit registers, since T is used internally for things. So if we want to copy information from one location to the next, the very basic string copy, which is a staple of almost all of people's early use of C, is to copy a string from one location to another. To do that in this system, we need to pass two 16-bit values, and we can't do that with just registers. And again, doing it with globals is doable, but kludgy, right? what we really want to do is make it totally portable so that we can pass those values in such a way that the calling function can get to them without having to have a hard-coded location or a hard-coded variable name. So to do that, we'll use the stack. And the example of that is actually here, where we're going to copy a string from ROM into RAM, and then we're going to copy that string from one location in RAM to another location in RAM, and then print out those different results. So this is probably going to be a little flipping back and forth here, but let's go ahead and get that going. Here's where we printed the last page of RAM. Let's see. All right. So now we're going to, again, we're going to hit the wrong button. That's what we're going to do. Hit that. I guess I can just start with that. There we go. That'll get us there. There we go. Now we're down in the string copy test. So we actually, before we did this, we set up a few things. One, we defined a string of characters in ROM called ROM string. That string of characters is this string of characters here, with /n and /0 being substitutes for a new line character and the null terminator at the end of strings. This is used in the C library to know when to stop doing a string copy. It's when whatever you're looking at has a 0 in it. It's referred to as a null terminated string and is pretty much how C has operated for 50 odd years, 60 odd years. So we create that string in ROM with these two statements. And then we create a couple of more strings. This is a little prompt string to just say ROM : for us. And then here's another string for RAM. So ROM prompt and RAM prompt. And then we're going to create a block of memory set aside in RAM for a variable named RAM string. And it's going to have space for 40 characters. This hopefully is not more than 40 characters up here. I suppose I should check. What do you know? That's column 40. But these two don't count and these slashes don't count. So it's enough space for us. Now we've got that. And we're going to actually do this copy test. So the first thing we do is load the location of the ROM string into the DR register. And we're going to put that value on the stack. So what that means is that we have 0335 here, and we want to put those on to the stack, which is the tail end of RAM, first pointed to by FF. So let's see if this shows it or if we're going to have to single step it even further. Now let's see if we do one step. You'll see that the stack pointer has decremented it. Anytime we store a value using the stack pointer, it decrements the stack pointer for us. And that's just a convenience because by and large, when you write using the stack pointer, you're going to go to the next location. So it automatically does that decrement. Unfortunately, it does not show that now the last byte of RAM should be the 35 value. Actually, the 03 value. No, yeah, the 35 value. No good way of showing that. But trust me, those two values are being put at those two locations. So basically what I've said is, using the stack pointer, I've used 2 bytes in the tail end of RAM to store the value that was stored in the value, or stored as the address. Stuck that all over again. I took the address of ROM string and stored its address in the last 2 bytes of RAM using the stack pointer to point to the next byte that I'm going to use. So we're going to do the same thing with RAM string. We're going to load the address of RAM string into the DR register, which is 000A. Then we're going to store R based off of the stack pointer, this is store the C in stack because I was running out of letters, and the R register. So store based off of the stack register, the R register. So here's the R register. We store it at location FFFD, and we decrement the stack pointer all in one command. Now we store off of the D part of the DR, which is 00. And now we can call string copy constant.
What?
I'm thinking how to show this. See, the problem is it's only during. So normally this line here shows what's in RAM based off of this register. So that's why it shows 0A. So it's the tail end of the register. So this is the line in RAM starting with 00 that contains 0A. And that's the highlighted one is that location. But the stack stuff is all stored on the stack and is just kind of hard to see because we only very temporarily look at RAM when we do the stack storage function. So a little hard to visualize without being able to see the stack contents. But we have a command for that. We have a command that toggles whether we're looking at either the RAM bank, the ROM bank, which is what this asterisk indicates, and whether or not the address we're using for RAM is either the data register or the stack pointer. Right now it's the data register indicated by that asterisk. But we have a command for that. The command to switch from the data pointer to the stack register is one of these conveniently complex commands. Not really. Let's see. Data moves. Let's see. We got no operation, halt, interrupt raising, masking, unmasking, decrement, increment, stack. There we go. TDS is the command. And that is not what most people would think of TDS is in the modern era, but TDS is the instruction that toggles whether we're looking at the data register or the stack pointer. So what I can do for the convenience of showing it, what we can do is before this, let's call TDS twice because we don't want to leave it like that. But that should allow us to see it. All right. Rock on. Reassemble. And it's... Ooh, don't do that. Anybody see what I didn't do there? No, you didn't. But I did. I didn't save the file. If you don't save the file, the changes don't apply. Save the file. Rerun it. Now let's just run it to that place again where we're about to do. Yeah. Now we copied the ROM string. Going a little too fast. Copy the ROM string. And we get the RAM string. Ah, dang it. This is why I add halt in there a lot. You might see halt in the code a lot of times. And it is because I want to be able to quickly run up to where the spot I'm interested in. So let's add another halt instruction, make sure we save it. All right, now there we go. So we're back to where we started. And we had just finished putting these two locations onto the stack. So let's see what happens here. There we go. We toggled the DR and the stack SP registers, so we can now look at the last line of the stack and see that we have 0305 stored there and 000A stored there. And the next location that we're looking at on the stack is this one. And so that we don't see, will it harm it? Will it harm it if I don't limit? Let's see what happens if I just, we're not going to. Let's just go ahead and let it, put it back. Correct it before we make the function call. But now, how can I make that more readily available? I really need to be able to, should probably add a command here. Like we have help and reset, run, return, halt, step tick, and steps. Should probably have a way to do that so we can investigate memory like this without having to call this command. Maybe later. That kind of works for now. All right. There we go. All right, what do we do? Oh, we're in the middle of the string copy function. Okay. All right, so all right. So the debate is, do I modify the emulator to allow us to do that for visualization purposes with maybe, I don't know, some other function key, maybe F2. What do you say? Maybe F2 toggles that for us? Thinky. Well, let's see if we can do it quickly. Let's do some code modification on the fly, shall we? Let's see, that's our emulator. It's not really visible, is it? Let's make it a little more visible. All right. Here's our keyboard thread. Here's our F1. All right. So that's what F1. So more than likely, 60 is F2. That would make sense. And that's going to be toggle DR SP, the data register in the stack pointer. So this is just going to force the emulation to do it for us so that we can do it on the fly and then see things work. So, of course, that's not what we want it to do. We need to figure out what we want it to do. So let's see. There's our chip core. Chip core. Well, someone's at the door. It's got to be some sort of, I don't know what. Who knows? Look like I'm cross-eyed. Yet another package. So let's take a look at our chip core. See if I remember. It's been a little while. Do I have... My chip core does not allow such. Which is to say, I never thought I would do this separately, so it's not in the program. But can we do it? Let's see. What would we want to do? Well, let's see. Chip core process is where it actually runs through each instruction and does different things. So let's see. Process sequence word. No, we don't want to do that. Yeah, I'm like staring off at the other monitor, but it's much easier to read over there. Trying to think here. It's one of those things I probably should have thought of earlier. All right, well. Actually, it isn't in that so much as it is in... So the TDS command would toggle the stack pointer and the data pointer in the processor itself. I actually don't want to do that because I have to put it back. Really, I just want to change the way it's displayed here. So there's the keyboard thread, and then there is the main thread. And I believe it's just called DRSP. No. Oh, no. It is in the keyboard thread. Yeah, I think it might even be called DRSP. So that's that state of the processor itself. What to do is overwrite it. So, right. So here we are. Where we print it out. Yeah, let's do it this way. We're going to create a temporary variables. And no, I don't know. I don't know if I want to do this here. And now,
Oh, you can start the next one. That was an hour.
yeah, I don't know. Let's see. Yeah, I guess so. We'll do it here about. So we want to show sort of force stack pointer, if you will. So we want to show SP, I guess we'll call it. And to be more exact, we'll say force show FP. Where, regardless of what its stated is, we show it. So there's that. And down here, where we actually don't do the chip anything with the chip core, we just change this flag. And we can say that. And that basically says take this value and make it to whatever is the inverse of that value is. So this one line, if this is true, it'll set it to false. And if this is false, it'll set it to true for us. So that's a quick turn on and off. And then here where we show it. Let's just create a temporary. And oops, the other way around. All right. So that's forced. Now it's going to be all backwards. It's not whether it's forced. It's just temporary tog DRSP. Just call it that. All right. So if we're forcing the showing of the SP, then we are forcing that toggle to be, I believe, true. Say true? Oh, we can tell by this. So that first value is this character here. So if that is true, then we're printing a 0. So right, so the default is the DR. So if we're forcing that, then we're going to force it to true. Otherwise, it's going to be whatever it would normally be from the processor. So that convoluted thing says create a temporary variable. Make that temporary variable equal to this question. Force show SP is true or false. If it's true, then set that to true. If this is false, then set this to whatever in the world this is, which is also either true or false. Now we use this in our characterization, these flags here. Instead of that directly, we look at the temporary version. What now? There we go. All right. So now instead of that other parameter, we're using this parameter. So this parameter is either going to be true if it's forced, or whatever it happened to be in the processor if it's not forced. All right. So that's that aspect. Now the next aspect of it is next location for tog. Next location is here, where we would use that to determine our RAM address, but instead we'll use the sorry. Instead we'll use this temporary variable, and that should do it. So now let's just go ahead and well, let's just build it. Build and build. And it said successful. Trust me, it's behind my back. And now that that's done, we can just, we don't even need to reassemble, let's just rerun. All right, now, big test. Seems like it don't work to me. F2 is not doing the thing we wanted to do. So let's go back over here, release 64. That might not be doing it. Let's do debug. Might not be copying it out to the other location. Although it does say one file copy. All right. It's not working. I hate when it's not working. All right. Now we're going to get into the real debug of it all. We want to stop it. Well, we don't want to stop at that point because this thing is going constantly. So let's stop where we hit the F2 because maybe we got that wrong. Let's see. And I don't know which program this is going to execute, but it doesn't really matter. No, string lib test is what it's executing apparently. Let's go ahead and make that our language. And it's doing a lot smaller when I'm doing debug. Let's see, F2. Oh, what do you know? It's not responding to the key. Responds to F1, okay. Sorry. Why don't it like F2? Well, I suppose it's because that's not happening. Seems kind of weird. F1 is 59, F2 should be 60. 61 would be F3, right? Don't you think? That should be how it is, right? Let's just set a sanity breakpoint. Oh, wait, there we go. It's actually showing us those breakpoints aren't applying for some reason. So this build is up to date. Why are you giving me bad breakpoints? Those symbols have been loaded. Weird. Oh, of course. Now Visual Studio wants to give me headaches. What is it doing that is not... Yeah, this was definitely not part of the plan. Start modifying things on the fly. Yeah. Let's see. Well, there's 3 watching. That's one more. Probably Dana. Oh, let's see.
Say hi to Dana.
Bye. Thanks for joining.
Watching.
Yeah. I'm assuming you can still hear me.
Yes.
All right. Let's see. Now, why in the world is it not stopping on that line? Why is it not? Build. Rebuild solution. When in doubt, rebuild. Ah, here we go. It's behind my head, but cannot execute the process because it is in use by other people's. So you can't update the program while it's running. So you got to close out the old copies. Make sure there's no other copies running. Now we can build it. I need to rebuild it. Who's complaining? Yeah, okay. Now we're behaving. Now we got solid breakpoints. So if we hit F2, we hit the breakpoint. Yay! So that actually works. Oh, well, it's not working, and it is working. All right. So yeah, we're talking there. Okay. So the problem was we just had the program up and running in the other window, and that was keeping it from actually copying and thus updating. So now we should be good to go. All right. Run this guy. Let's try. Yep. Although both locations are empty or don't show any difference. So let's run some. All right. Halt the instructions. I don't know where it's at, but let's jump out of that. Ooh, ain't that fun? Yeah, it makes me snort. It's going so crazy. Halt. All right, now let's see if we can. There we go. Now we can tell the difference between what we're seeing here. And oddly enough, we're actually in a function where we executed a command to swap the data register and the stack pointer. And so that's why now we're seeing the stack pointer value, even though it's looking at it's all just backwards. All hail the great binary everything. All right. So now that works, let's talk about what we were actually talking about. Let's go back over to parameter passing 3. Spin her up. And now that we can toggle back and forth between which bit of RAM we're looking at readily, let's go ahead and run through these first parts of the program until we get here. And actually, start that over one more time. Get to there. There. All right. All right. So now we want to pass our parameters on the stack. And to do that, we're going to load the address of the ROM string into the DR register. Now we're going to store it on the stack. And to see that, we'll switch over to the stack view. And you'll see we're about to store the contents of the R register on the stack, which is to say we take the 35 here and store it wherever the stack pointer is pointing, which is there. And then we've also automatically decremented the stack pointer. So now we're store the D register out here, which is that 3. And again, it decrements. And what's happening is the stack pointer is decrementing from the very top end of RAM, all Fs, grows downward. Or I should say it starts at the top of RAM and grows downward. And your RAM, your programs, and your RAM you assign to variables starts at the bottom of RAM and grows up. So you might want to say, what happens if your program or your stack pointer gets into your program? Obviously, lots of bad stuff happens. So neither the twain shall meet, but what it allows you to do is build your program up from one end and then allow the stack to grow and shrink as needed on the other end of RAM. In more complex programs and operating systems, there's a separate batch of memory set aside for the stack for each function, or rather for each process or thread. So we've loaded up our ROM string onto the stack. Now we're going to load RAM string. We'll load that into DR first. Then we're going to write the OA out, the R. Now we're going to write the DR, or the D value out, which is 0, 0. So we overwrite those previous values that were on the stack. We did the halt to show those twice, which we no longer need. So now we're going to call the function string copy constant. And then as part of calling this function, we have to know where we're going to come back to after the fact. And that value is stored on the stack as well. So when we jump into this function, you'll see we actually stored 2 more bytes on the stack, and that's the location to come back to when we're done with the function. And so that's the extent. You see the rest of these are 0. That's the extent or the depth of the stack so far. So now this function is going to load up. In order to read the values from the stack, it has to know how far away the value is. So in this case, coming into the function, we know that there should have been 2 values stored on the stack, each 2 bytes each. And then there'll be another 2 bytes for the return location. So that means that the source parameter that came into this function is stored at 6, meaning 6 bytes, the stack pointer, plus 6 bytes. So wherever the stack pointer is now, plus 1, 2, 3, 4, 5, 6, and sure enough, that's the location of the first little Indian byte of the source location. So we're going to call string copy source 6. We're going to create that constant. And then we're going to call the instruction POE. And what POE does is it copies the stack pointer into the data register and then adds that 6, the next value passed, to the data register. And now we have this location of our source parameter. But it's the location on the stack of our source parameter, which is a location in memory that we want to copy from. Hence this concept of a source. So we're going to use this little triple dance again, where we first load the value pointed to by the DR register in RAM, which in this case is interesting. There we go. Let's move our pointer back over. So now we're looking at DR. Our RAM, rather, is looking at DR. So it's looking at 35. We're going to load that into A. Then we're going to decrement the stack pointer. Again, the stack pointer grows downward and the normal memory grows upwards. So we're going to decrement the stack pointer, load the next value directly into D, and then load the value from A into R, and that gets the location. Now that's the location in RAM, or rather the location in ROM for our source string. Remember, this function is string copy constant. So we're string copying from a constant in ROM into RAM. So the next step we do is we're going to load a byte from ROM pointed to by the DR register into the B register, which is the value 54, which is the first character of our string. And since that value loaded into B set our non-zero flag, we're going to jump back to the string copy constant, or jump to string copy constant rather, where we continue operating on the string. So we did we loaded that first byte from ROM. Now we're going to, and it wasn't 0. So now we're going to load the location and the destination. And that location and destination is 4 bytes from the stack pointer. So we will load the stack pointer into DR and add 4 to it. So now we're pointing at the next variable that we passed, the destination variable. Do that same little rigmarole to get that value into the DR register. And now we're going to store what was in B in that location in RAM. And there's our 54, sure enough. So again, we now increment the data register, the destination, and we're going to store that new destination. So in order to do that, we have to store the value of DR into A and B. Then we load the destination location, store the value for A. Oh, yeah. Load the value of the destination from the stack pointer. So we're basically reading from and writing to the stack pointer as we change these addresses, as we move from one location in the string to the next. We need to change the source location by 1 and the destination by 1, read that next byte. If it's not a 0, copy it over, and continue doing that loop until the byte that we read is a 0. This is how all the string functions operate in the C language. They just keep going until they run into a 0. And there's just a whole slew of problems that have created security issues, all sorts of mess that has come from this rather simplistic way of handling strings that has been around since the beginning because it is fairly efficient. It's only a few lines of assembly necessary in order to copy strings using the null to know when they end. But basically, the simplicity was done due to necessity of these kinds of levels of processors. We could certainly do better if we started over today, or so we think anyway. All right. So now we're going to finish off. Well, we stored that byte. Now we have to change the destination address, or store that value in the destination address. Load the source address again. Increment that source address. Store that source address back where it was. So now we have the incremented version. So these 6 or 7 instructions are what are necessary to implement variable equals variable plus 1. And so since there was something other than a 0 on that last byte, we're going to keep going around in circles. Let's run until we jump out of that. So now we called that function. It did the copying for us. And now that we did that, we had taken up some space to pass the parameters on the stack. Now we want to give that space back to the stack so that we're not wasting space, and those same bytes can be used later to pass a different parameter. So to do that, we actually just implement the increment stack instruction. Because the bytes are there, we don't need to zero them out. We just need to move the stack pointer back to where it was before we called the function. Otherwise, we start eating up stack space and eventually run out. So there's passing the parameters on the stack. Now we're going to print the line from the ROM. So we load the ROM prompt, and we just call this function that prints those things. So it printed out ROM colon. Now we're going to load the ROM string, and we're going to print the ROM string, which is, this is a string that is in ROM. How convenient. Now we're going to print the string that we had just copied into RAM. So we're going to load the RAM address, or the RAM prompt address first. Print RAM colon. Now we load the actual RAM string, and we print it out, which is sure enough, this is a string that is in ROM, but it isn't in ROM, it's in RAM. So we want to change that. So the way we can do that. Oh, and I hit the wrong button. Wrong button hitting. All right, so as you see now, it says this is a string that is in RAM. Ooh, miracles. Okay. Let's just get her started back up at that point, shall we? All right. I'm going to run to that halt line, 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 and there we are. Don't hit the button. Do not hit the wrong button. Okay, so as you see, we copied the string from ROM into RAM, but it still says it's from ROM.
It just keeps hitting around.
So what we need to do is we want to load the address of the RAM string into DR, and then we're going to load the 31st character position, which is to say all the way, what is this O, right? So we're going to load that into the A register. And now we're going to sum. The E stands for summation symbol. the D and the A register together. And then we're going to load the constant A into RAM, or into A rather. Load the constant capital A into A. And then store that value where we're pointing, which is right there. And now if we load the RAM string again and print it out, it now says that it is in RAM instead of ROM. Well, I think that's more or less what I'm somewhere in all of that. Hi, Dana. I just saw it in the chat. All right. I think I can cut together something useful out of all that.
Yeah.
More or less.
Awesome. I'll tell everybody thank you for watching and all that good stuff. Ring the bell.
Ring the bell. Ring the bell, and thanks for watching. And let's see, did I have some other things here?
Don't push the wrong button.
Don't push the wrong button. All right. So there was one other thing I wanted to talk about, and that is, let's see, do I want to do it like this? Do I want to do it like a short? Thinky, 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 think. All right. So while the 5108 virtual microprocessor or microcontroller could be possibly built out of actual silicon, it would be rather expensive and somewhat difficult for me to do on the time and budget schedule I have. So what I did think was I could probably make something of an art piece out of this by putting little LED displays on a canvas, and just might as well just let the electronics show. And take what I've been using as an emulation on Windows here and put it onto something like a Raspberry Pi or a larger Arduino, and then let that larger Raspberry Pi or Arduino fill out these values. So I get something close to a hardware version of my processor, something more like an embedded processor version of my processor. But it's going to be something like 9 by 12 inches. Each one of these little LED displays is this big. Well, that's interesting. What's that do? All right. So by the time these are all on the board like this, it's going to be about 9 by 12 inches or something to that effect. And that'll be an interesting little poster board or framed version of the processor. And so the circuit board with all the LEDs are being bugged out of China right now from JLC PCB. So we will see those shortly. And what those are based on is this. Let's see. All right. So each of these two dual LED displays displays a single byte in hexadecimal, the same system we've been using. And it's actually based off of this little bit of electronics that I built some 3 or 4 years ago called the TLA display. And what it's doing is this. Whoop. Let's not do that. Interesting. All right. There we go. Now, okay. So, So these displays are actually based off of this bit of electronics I did a few years ago called the TLA display, where this little area here is the microprocessor, and it is driving a row of LEDs and a column of LEDs, and it's just pulsing through them, running through the rows over and over again very quickly. And not terribly quickly, because this whole system called Tinkercad is fairly slow. So what you're seeing is actually a sped up video of the electronic simulation. Now going from there uh, to a single hexadecimal display like this one, where you have a small external processor that's actually sending signals to another small processor that is sending values out of these two drivers to drive the two displays. So this little circuit duplicated 25 times is what we're doing for this larger one. In fact, this is a simulation of having multiples of those displays tied together. All of that's up on Tinkercad, so if you like and subscribe and you like what we do here, you can check us out on Tinkercad, on Thingiverse, where a lot of the 3D models are. And in any case, I hope you enjoyed the show, such as it was, behind the scenes and super raw. And
Taking and doing.
I hope you join us for the final cut version, which will probably be like 10 minutes long or something. Anyway. Alrighty, y'all. Thanks for joining. We'll see you next time. Bye.